Hello, everybody. Good afternoon for our colleagues in German, and good morning for our Brazilian colleagues, as it's about 5:30 a.m. over here. I'm Vinicius Bufon, a research scientist from EMBRAPA, which is the Brazilian National Institution for Developing Sustainable Agricultural Production Systems. I'm an agricultural water use efficiency specialist, working mostly with energy crops. And I'm a practice partner of WANDEL project for the biomass electricity case study that took place here in Brazil with the Brazilian sugarcane case. Well, sugarcane crop use for sugar production is now for centuries. Sugar cane ethanol as a biofuel was firstly used in Brazil around 1920, I would say. In the 70s, the Brazilian government launched the national-wide program to promote sugarcane ethanol production as one of the main sources of our energy matrix. And once crushed, sugarcane juice is directed to sugar and ethanol production. And the bagasse, the fiber left over, is then burned to generate steam, which is used in the industrial processes, and also to generate electricity to cover sugar mills' needs. But there is an enormous surplus of sugarcane bagasse. Decades ago, to avoid piling up the bagasse in the outdoors, intentionally low efficiency designed boilers were used to burn out the surplus bagasse. By connecting the sugar mill to the national electricity grid, instead of wasting the bagasse energy, it became a more useful, environmental, sustainable, and economic efficient electricity source.
Vinicius?
EMBRAPA, as the Brazilian National Research Institution, had the mission to develop more sustainable agricultural production system. And this is the reason why we started using water footprint methods to analyze sugarcane and ethanol. And with WANDEL project, we were challenged to expand our studies to sugarcane electricity. We were very successful joining EMBRAPA's and United Nations University team's expertise to run very detailed and actual field data-based water footprint calculations. We basically separate our calculations in two phases. The first one is the sugarcane crop footprint, and the second one is the sugarcane process footprint. And we joined it to encompass our direct water footprint for sugarcane. We actually could even expand our studies to analyze draw risk assessment, encompassing also interviews with local farmers, sugar mills, policymakers, and briefly showing our water footprint results. I'm showing here two scenarios. One is the 2010 scenario, when we first started developing more water use efficient sugarcane production systems. And within the 2010 scenario, you can see three different production systems. The first one is rain-fed sugarcane, which is just dry land sugarcane. As you can see, most of the water footprint comes from the agricultural green water use efficiency, water footprint. You can barely see a very thin line the top of the big green bar, which is the industrial water footprint. It's very, very, very small compared to the agricultural water footprint. The second production system is what we call salvage irrigation. Sugarcane in Brazil is harvested in the middle of 5 to 7 month dry period. after we harvest the sugarcane, it has to reshoot to be harvested for 1 more year. But because of the draw, there's no a lot of water available for sugarcane to reshoot. So one of the technologies is applying one single irrigation depth to allow sugarcane to reshoot, and we call it salvage irrigation. As you can see, as we move from rain-fed to salvage irrigation, you increase overall water footprint at an expense of a little bit more blue water footprint. As we move to the third production system, it's called here full irrigation in the chart, but it's actually a control depth irrigation production system. At an expense of more water footprint, we can increase overall efficiency and reduce overall water footprint. As we develop more technologies and we improved yield and efficiencies, we moved to the EMBRAPA's enhanced 2019 scenario. As you can see in the rain-fed, salvage irrigation, and depth control irrigation production system, we were able to drastically improve our efficiencies. But one thing should be said here. We can improve water's efficiency through irrigation, but at an expense of more blue water footprint, which drive us to the conclusion that in order to achieve higher efficiencies, lower water footprints, we must have a very well-managed water resource system. Otherwise, we could end up in the worst scenario. As by one side, we have a lot of fresh water availability in Brazil, but on the other hand, we also have several areas with already water availability restrictions. Water footprint tools are very good for helping us to identify the efficiency bottlenecks, improvement opportunities. It can be used to compare the efficiency of new technologies for every piece of the production systems we improve. And we also use it to monitor regional water efficiency over time. But its best use only happens when we couple it with water availability. So we can use water footprint finally as a sustainability assessment tool. I would like to especially thank GRoW Initiative and the United Nations University for the solid and true collaboration in this project. It's been an exciting and fulfilling journey, and we look forward for more projects and partnerships like this. Thank you very much.